1.57. In this lecture, I will explain ripple factor and we will find out the general expression for ripple factor, and by using it we will calculate the ripple factor for half wave rectifier. The output current contains both AC and DC components. This is something I have already explained. The output current contains both AC and DC components. The ripple factor measures the percentage of AC component in the rectified output. The ripple factor measures the percentage of AC component in the rectified output. So by using the ripple factor, we may represent the percentage of AC component in the rectified output. Ideally, the value of ripple factor should be 0. The value of ripple factor gamma, ripple factor is represented by gamma, is equal to 0% because we want our output to be 100% DC. We are converting the AC to DC and we don't want any component of AC in our rectified output. So we want AC component equal to 0, and when this happens, this implies the ripple factor is also equal to 0. So let's try to obtain the general expression for ripple factor. The ripple factor gamma is equal to RMS value of AC component of output divided by the average value of output. First I will calculate the RMS value of AC component of output, then we will divide it by the average value of output. Let's say the total output current is equal to I, and it is equal to IAC plus IDC, the AC component plus DC component, and this implies IAC is equal to I minus IDC, and we already know how to calculate the RMS value. The RMS value of AC component, that is IAC RMS, is equal to the square of IAC. Then we will calculate the mean by integrating it from 0 to 2 pi with respect to d omega t divided by 2 pi, and finally we will take the square root. This is the RMS value of AC component. Now I will simplify this. IAC is equal to I minus IDC, so I will replace IAC with I minus IDC whole square d omega t. 1 by 2 is the representation for square root. We already know this. A minus b whole square is equal to a square plus b square minus 2ab. In this case, a is equal to I and b is equal to IDC. So in next step we have 1 by 2 pi integration from 0 to 2 pi I square plus IDC square minus 2I IDC. This is what we have, d omega t 1 by 2. In the next step I will integrate them individually. So we have 1 by 2 pi integration 0 to 2 pi I square d omega t plus integration 0 to 2 pi, here we have 1 by 2 pi IDC square d omega t minus 2 divided by 2 pi integration 0 to 2 pi IDC d omega t 1 by 2. And we already know IRMS, the RMS value of load current, is equal to I square integration 0 to 2 pi d omega t 1 by 2 pi 1 by 2, and if we square both the sides we have IRMS square equal to this, and this is similar to the first term. So I can write IRMS square in place of this term plus I dc square is constant, and if we integrate the constant term, let's see what we have. A is the constant, dx, then the integration is equal to ax. In this case we have I dc square d omega t, so the integration is equal to I square dc omega t. But we have 0 to 2 pi as the limits, 0 to 2 pi as the limits. 0 is the lower limit, 2 pi is the upper limit. So here we have 0 to 2 pi. So finally we are getting I dc square inside the bracket 2 pi. But here we already have 1 by 2 pi, so this 2 pi will cancel out, and we finally have I dc square. In the same way you can integrate this term and you will have twice of I dc square 1 by 2. I dc square minus twice of I dc square is equal to minus of I dc square. So in next step we have I rms square minus I dc square 1 by 2. This is the RMS value of AC component, IAC RMS. We have our numerator now. We have our numerator. It is equal to I RMS square minus I dc square 1 by 2, and we already know the denominator, which is average value of output, is equal to I dc. Very simple. Or we can write it like this: inside the bracket I RMS square minus I dc square divided by I dc square 1 by 2. When I dc is taken inside the square root, it will be I dc square, and we can simplify it like this: I RMS square divided by I dc square minus 1 by 2. And in the last presentation I told you form factor is equal to I RMS divided by I average or I dc. So I RMS square divided by I dc square we can write as square of form factor minus 1, and everything will go inside the square root, and this is equal to gamma. Gamma is the ripple factor. So this is the generalized formula for the ripple factor: under root form factor square minus 1. I will use this formula to obtain the ripple factor for half wave rectifier, and in terms of percentage, gamma percent is equal to under root form factor square minus 1 multiplied by 100. We already know in case of half wave rectifier the form factor is equal to 1.57. This is the value of form factor, and we can calculate the gamma is equal to under root 1.57 square minus 1. When you solve this you will have 1.21. This is gamma, and the percentage ripple factor is equal to 121%. So you can see we have 121% of AC component in the output current. This is very high value, and we don't want this much of AC component in the rectified output. This is one of the disadvantage of half wave rectifier. I will end this lecture here. In the next lecture we will discuss peak inverse voltage and efficiency of half wave rectifier.